In this video, we'll be discussing Factorial ANOVA. As we mentioned earlier in this lecture set, one of the valuable attributes of ANOVA is that it can handle multiple independent variables, which allows for a couple of important things. First, we can analyze the effects of multiple independent variables on the outcome using a single data set, which can be very important and efficient, especially when data on a particular topic are hard to come by. Second, we can determine how the independent variables impact on each other's influence on the dependent variable. This is called an interaction effect, and ultimately it'll look like one independent variable influencing the relationship between another independent variable and the dependent variable. One weird thing with this that we'll get into in a little bit is we actually don't know the direction that this goes in. So this could go, variable 1 could influence variable 2's relationship with the outcome, or variable 2 could be influencing variable 1's relationship with the outcome. The analysis doesn't indicate either of those. You'll sometimes hear these called by one-way ANOVA or two-way ANOVA. The number of ways simply indicates the number of independent variables. So, for example, in one-way ANOVA, we're discussing one independent variable, while in two-way ANOVA, we're discussing two independent variables, and that's going to be what we focus on in this lecture video. Generically, ANOVA with multiple independent variables can broadly be called Factorial ANOVA, and that covers multiple independent variable ANOVA, no matter how many ways the ANOVA would otherwise be. Now, I mentioned interactions before. This is actually a really important concept. It's new in this class, but I believe, I don't think we've talked about this yet, but is again something that's very, very important in terms of its implication on the results. So again, this is when one independent variable, or both mutually, impacts the relationship between a second independent variable and the dependent variable. Again, we don't necessarily know, the analysis doesn't indicate which direction this goes, and depending on the study design, this could go in either directions, or it could go in both directions at the same time. Sometimes this type of effect, an interaction effect, is called moderation, depending on who you talk to and the nomenclature that they're more familiar with. While we often analyze this explicitly when we're analyzing data in two-way ANOVA or more, it's important to realize that this concept is always possible with multiple independent variables. In fact, you can run two-way ANOVAs, three-way ANOVAs, four-way ANOVAs, in general, factorial ANOVAs, without interaction terms. But if you do this, you're adding an assumption to the model that the interaction effects are zero. And that may or may not be correct. In fact, by making that assumption, you could be missing a major finding within your results. I'll mention here too, as I've mentioned it in the earlier bullet, interaction effects can be calculated with multiple way ANOVAs that are higher than just two. The interpretations I've been discussing thus far and will discuss through the rest of this lecture video will relate to two variables, one independent variable interacting with the other, but interaction terms can be calculated for higher number of interactions. The problem with this is these become immensely difficult to interpret, with many researchers choosing to not include interactions higher than two or three-way interactions, that is, interactions between two or three variables, because of the complexity of interpretation. Ultimately, this comes down to the context and the situation. But let me challenge you that if you're reading through an observation or a statistical analysis that utilizes multiple interactions, be careful, especially if they are higher than involve interactions between more than just two variables. These are notoriously tricky to interpret. Now, to get a feel for what interactions are talking about, I want to show a few graphics of results. Broadly speaking, this style of graphic is going to be called an interaction plot, and is if there is a statistically significant interaction within the analysis, probably the best way to then interpret the results. So within the context, I'm going to be looking at men and women and their satisfaction with their hospital visit, depending on how long the visit was, or excuse me, their doctor's appointment, depending on how long the visit was. So I've got short visits and long visits. In this particular plot, what we see is the short and long visit are actually the same line. There's no difference between short and long visits in terms of satisfaction. And we see that men and women are at the same level too. There's no difference between men and women in terms of satisfaction. So this is an example of an interaction plot that shows no difference between men and women, no difference between visit lengths, and no interaction. And just as a heads up, we're going to go through some basic plots before we get to the interaction plot. So don't anticipate that these initial ones are demonstrating interactions. We're going to just discuss what the general interpretation of the plots are prior to getting to the interaction interpretation. It'll be our last one. In this plot, again, looking at the different lines, I see that they're, in this case, the lines are the same. They overlap each other. I'm staring at my screen really closely to see if I can see the tick marks on this line. I don't think I can at this resolution, but again, these lines are overlapping with one another. We've got the short and the long visit. There's no difference in patient satisfaction is what this suggests from this analysis, and that men are less satisfied than women. Interestingly, this implies men are less satisfied for both short and long visits. Men are just less satisfied in general than women in patient satisfaction. And that would be the correct interpretation of this particular plot. For this plot, we see finally a break in visit length. We see, in this case, the suggestion is that long visits have higher satisfaction than short visits. But notice if I look from left to right, men and women don't have a difference. And it's not just that they don't have a difference on each individual line. If I took the average male satisfaction, it'd be in between my short and long visits, assuming equal numbers of each. If I took the average women's satisfaction, I would take the average of these two. And again, both of these average values would be right in the middle, indicating about average satisfaction. That's not what I'm interested in. Here, I'm trying to indicate that the male and female satisfaction would be the same on average between the two. All right, so we've discussed what each of the individual components are going to look like. We still have one more image to look at before we get to the actual interaction image shown in an interaction plot. And that is what happens if we have a difference in both variables. So in this case, what I want you to notice is that if I looked at the average male score, it's about in the middle here, the average female score in the middle here, again, assuming equal group sizes, and that indicates that the average women's satisfaction is higher than the average men's satisfaction. For whatever reason, women are just more satisfied than men with their visits, would be what this suggests. I can also see that for short visits, the average patient satisfaction for short visits is about, so left to right is difference between men and women. Up and down is satisfaction, and again, this dotted line is short. So really, I'm trying to get about halfway here, up and down on the short line, and it can be off the short line. It doesn't really matter. About halfway between the top dot and the bottom dot on short to indicate what the average short satisfaction is. And then same thing for the average long satisfaction, about halfway between the bottom and top dot. Average long satisfaction is about here. So in this, again, we're seeing average short satisfaction, average long visit satisfaction, that for that on average long visits we're getting higher patient satisfaction for. And that would be the interpretation of the distinction between the visit lengths and these lines Note that this effect is consistent whether you're a man or a woman. Men prefer longer visits, and women prefer longer visits. So that would be the interpretation of this particular interaction plot. All right, now let's look at an interaction. And this is what an interaction looks like. Ultimately, consider, do men or women, which one's more satisfied? And if you look at the average male score, you'd see it's here, and the average female score is here. The temptation is to say, well, they're the same. But if you compare this to what we saw earlier, they're not actually the same. If you look for short visits, women are way less satisfied. If you look for long visits, men are way less satisfied. Women are more satisfied. So the answer of which one is more satisfied, males or females, kind of depends on the visit length. Now that's probably an ancillary question. Probably of more interest is looking at the visit. Which one are patients going to be more satisfied with, short visits or long visits? And here, what this graph would suggest is, well, if I took the average long visit, it'd be right here. The average short visit would be right here. Oh my gosh, there's no difference between them. But again, if we look at this graph and we interpret this, we see that's not actually true. For short visits, males prefer short visits. Short visits, patients can be very satisfied with short visits if they're male and very dissatisfied if they're female. For long visits, patients can be very satisfied with long visits if they're female and very dissatisfied with long visits if they are male. This is the point of the interaction plot. The conclusion is that it depends. Do short or long visits result in higher patient satisfaction? Well, in this case, it depends. Is the participant a male or a female? For men, according to this graphic, men prefer short visits. For women, according to this graphic, women would prefer longer visits. And this might have some implications on how we address the situation. Notice if I just looked at short versus long, there is no difference. And if I just looked at male versus female, there's no difference. But when I take and analyze them after accounting for the other one, I see that actually there are some differences here. It just depends on the other variable. That is, the difference between short and long depends on what the sex is. And the difference between the sexes in terms of patient satisfaction depend on whether or not the visit was short or long. So this idea of it depends is the whole point of an interaction interpretation. And these interactions impact interpretations, absolutely. Again, the initial interpretation, if I were just looking at the main effects, that is, I was just looking at visit length without accounting for sex, or if I was just looking at the difference in sexes and patient satisfaction without accounting for visit length, I would get answers that are deceptive in the sense that it would say there's no difference, when in fact there's massive differences after we account for the other variable. Because of this, and because interactions can have such an impact on interpretation, there's something that we actually need to check at the beginning. So when I start my analysis, I want to check on the interactions to see if there is an interaction effect. If there's not a statistically significant interaction effect, we can move on to interpreting the results normally. That is, I can just look at my sex effect and see, is there a difference between the sexes in patient satisfaction? I can look at the visit length and see, is there a difference in patient satisfaction between the visit lengths? On the other hand, if the interaction effect is statistically significant, that's an indicator that we can't really trust it, because it might be like that last graphic, which says, no, there's no differences between the sexes, and no, there's no difference between the visit lengths. When in fact, we saw within women, there was a massive difference between the visit lengths. Within men, there was a massive difference between the visit lengths, but they were differences in opposite directions. And again, it's too simplistic to say there's no difference in patient satisfactions for short and long visit lengths if what's really going on is there's massive differences, but it depends on whether the participant is a man or a woman. In that plot, women preferred longer visits and men preferred shorter visits. Now, sometimes interactions are viewed as a bad outcome, and they're viewed as bad because people misunderstand them. Oftentimes, interaction effects are either ignored in the model or, if included in the statistical model and calculations, are ultimately ignored in the results. People try to minimize them because they don't want to deal with the complexity that's involved. So they've gotten a bit of a bad rep, but ultimately they're not worse. They're just a little bit more complicated. They simply tell you that ultimately one independent variable needs a little bit more context than just short visits patients are less satisfied with the short visits than long visits. They tell you it's a little bit more complicated than that. And again, in our example that we worked through with that last interaction plot, it would say, yeah, it's a little more complicated. It depends on who you're talking to. Might be that if I'm working with a mother who has a sick child, they really want me to take a long time and make sure I look at every possible thing to help with that kid, and they want me to be in there for half an hour or 45 minutes. Of course, it might be if I'm working with a blue-collar worker, they're going to be most satisfied if they're in and out quickly because they don't really want to be in my office anyway. So it's just saying you need a little bit more context than saying short visits are bad or long visits are good. Maybe you need to look into this second variable and how those two variables relate with each other. I should mention, again, we don't know the direction that these go. So the last example is a little bit different because of the design of that particular study. But broadly speaking, we don't know which direction the interactions go, and they don't tell us which direction that happens in. I mention this because the graphical construction, I'm advising that you use the graph when you run into an interaction, a significant interaction, to aid in interpretation. That's where your interpretation should come from, is the interaction plot. But how we design that, which variable do we include on the x-axis, which variable do we do as the line, that can influence or imply a particular direction of interpretation. So really think through that, as with any other graphical method you create, that you're not accidentally implying something that you shouldn't imply. That is, you're not accidentally implying that the interaction is saying A impacts the relationship between B and C, when actually you don't necessarily know that that's the direction of that. It could be B that impacts the relationship between A and C. So just be a little bit clear on that and be a little bit careful with that, especially if you end up observing an interaction and seeing a plot. I was actually recently just in a presentation where somebody was studying an interaction effect and was very confused by how some variable could be influencing the relationship between A and B. How can this third variable be influencing that relationship? And didn't realize that actually it could be exactly the opposite. That variable's relationship with the outcome could be the effect, and this other variable that they were treating as their main independent variable could be the interactor, the third one that's impacting the relationship. So it goes both ways. And actually, in this particular researcher's situation, that other direction made a lot more sense. So it's something to consider. It's something to be aware of. Again, sometimes it's not even one direction or the other. It's both at the same time, or it's neither. It could be some underlying factor affecting the relationship. So just be careful, and again, be modest, as we've discussed in our statistical storytelling. Be modest with your conclusions when interpreting these, and understand that they can go in either direction. So if one direction doesn't make sense, if you're ever observing a report like I recently was, I think this was actually last week, don't hesitate to say, hey, could this go in the other direction? Because the answer is absolutely it could. All right, so for examining our nursing program, let's add in a second variable. So we're going to add in the demographic variable of sex to determine if there was a difference between the sexes on the exam score. But as part of this, we're also going to check, both as a control and as a second research question, if the effects of the program are different for the different sexes. That is to say, is there an interaction between sex and program on the overall score? Again, it's very important to note if you just run a two-way ANOVA without the interaction effect, which is possible to do. In fact, it's the default in most softwares. You are explicitly telling the statistical software that you want to assume that there is no interaction. It is always better practice, or almost always. There's no situation I can think of where it's not better practice. So let's just assume, for the intents and purposes of this class, it's always better practice to run the model with the interaction and allow the statistics and the data to tell you, nope, there's no interaction going on here. Because if there is one, it's one that you want to investigate. All right, so let's look at the results here. This is from, again, a different software, just pulling up some different ones so y'all can see some output from some of these different types of software you may run into. I think we've used Stata and SPSS, and I think this is R, if I remember right. So just throwing in a few different ones for you. So now that we know about the interaction effects, when I look at my ANOVA table, and that's what this is, an ANOVA table, you'll note that I have the residuals. R does not give us the total sums of squares, so it's a unique thing about R's ANOVA table output. But I have my residuals. This is the error. So instead of within, it calls it residuals, or instead of error, it calls it residuals. And then I have my treatment effects. So I actually have, instead of just one line, which previously was sum of squares between, or sum of squares treatment, I have three. I have the first variable and the second variable. And then I have a third variable, which represents the interaction between these two. Now that we know about the interaction effects, we know that we need to check them first. So the first thing that I'm going to do is look at the program by sex interaction, which in this software is indicated via the colon. I'm going to scroll on over to the p-value. Again, I'll skip over the sums of squares, the mean squares, the f value, and I'll just focus on my p-value here. The p-value, which in this software is indicated as PR with the greater than f sign, indicates that this is not a statistically significant interaction. So I get to just go on and interpret my main effects, knowing that there's not differential effects of these variables depending on the level of the other one. So I can just go on and interpret these normally. So going on and interpret sex, it looks like there is not a sex effect. That is, there is not a difference between males and females. In this program, I can quickly see males and females, two groups. 2 groups minus 1 gives me 1 group, so I can confirm that this is 2 groups that I'm looking at in terms of my sex variable. And again, not a statistically significant impact. This is what we like to see. The test should not be biased based on sex. So in this case, we can confirm that. For the program effect, we can see that this is still statistically significantly different. I can confirm, again, with my degrees of freedom, that I'm looking at 3 programs. The degrees of freedom plus 1 is the number of different levels here. So the program is effective, broadly speaking. So it's effective at increasing the score. Now, the cool part about this is that now that I've included the other variable into the analysis, I can take my interpretation one step beyond. So in interpreting the program, I can say that there is a statistically significant difference between the programs on the exam score after accounting for sex. And this is where adding this other variable in, I now get to include the language because I've accounted for sex in the analysis, that this is after accounting for that variable. And interpreting sex, I say that there is not a statistically significant difference between the sexes on the exam scores after accounting for program. So in terms of the program interpretation, that's kind of handy to say after accounting for sex, because that's something that you may want to account for. In terms of the sex interpretation, after accounting for program, that might not make as much sense. So I might want to rerun that one without program. I mentioned the interpretation, or excuse me, I mentioned the check of the interaction effect to make sure we could interpret main effects earlier. But the formal interpretation of the interaction effect in this context is that the program doesn't have different effects based on sex. So consider what interaction here would have meant. It would have meant that the program effect on the score changed based on what sex you were. It would have meant the program is more effective for one of the sexes than the others. Or if this were multiple sex groups that we used here, is more effective for one of the sex groups than the others. So we probably don't want that in our program. Our program, we'd like it to be equally effective no matter who's in the program. So this is actually a good sign saying we don't have evidence that our program has differential effectiveness based on what sex you are. Again, this is a null finding, but it's one that we didn't want to be significant. Just like we didn't want overall men and women to necessarily have different scores on this exam. So these are null findings, but are not necessarily bad findings. Again, we're able to make the conclusion about program after accounting for sex, which is a pretty handy thing. And we're also able to loosely make this claim. We checked if the program had differential effects for different sexes, and we didn't have evidence to believe that it has differential effects for different sexes, which is that's a great thing that our program would love to say. Note what I'm not saying here, and it's sometimes difficult to be careful. I am not saying we have evidence that our program doesn't differ by sex. That's not what we did. We assessed if the program did differ by sex and did not find evidence to support that. But that is not the same thing as having evidence that the program doesn't differ by sex. Those are different questions. So we failed to reject the null hypothesis. That doesn't mean we accepted or provided evidence for the null hypothesis. We tried to check if there was a difference. We didn't see one. But that's not the same thing as we have evidence for. So again, in this case, we checked if the program had a differential effect by sex and did not have evidence that that was the case. That's the conclusion. Again, it's a lack of evidence. It's not a presence of evidence that this indicates regarding that particular question. All right, well, this has been a discussion of factorial ANOVA and the frankly rather tricky concept of interactions and what we do within them. In the next video, we'll jump into the statistical assumptions that ANOVA makes and what they are and what we can do with them.